So we are going we are going to start off with this new chapter, magnetic effect of current. Magnetic effects of current. It's a very large chapter as well as important one, and it has this chapter has quite a lot of concepts and quite a lot of directional type of concepts. So be very careful with this chapter. There's a good weightage of this chapter in every exam. Okay. Now, magnetic effect of current. First thing in this is Oerstead experiment. So, what is an Oerstead experiment? So, Oerstead again was a scientist, as every other scientist back then. They used to experiment a lot, and out of experiments we found quite a lot of things. So, Oerstead did some experiment. Now, what is the experiment he did? So, what Oerstead did that was he passed a current in a wire. Okay, he passed some current in a wire, connected the wire to some cell. Okay, there's a cell here, as you can see, and some current was passing through this circuit. Okay, and what he did was put a magnetic compass just below this circuit. Now, when he put the magnetic compass below the circuit, he saw that because of this, when the current is flowing, this magnetic compass is getting deflected. Okay, when this current is flowing, this magnetic compass is showing some deflection, and this deflection is going to change when he changed the direction of the current. Then the deflection changes. Okay, when the direction of the current changes, then the deflection of this compass also changes. You see, so you see here, when the current direction changes, first the current was flowing from here to here. This was and then the current is now flowing from in this direction. So the direction of the deflection of the magnet changes. So this can be concluded that there is something which is causing the magnetic compass to deflect. And what causes magnetic compass or magnetic needle to deflect is a magnetic field. But here there is no magnetic field as such. So it was then concluded that the current which is flowing is causing some magnetic field, and the flowing current causes some magnetic field, and that is why this needle is getting deflected. So since the magnetic needle can be deflected by the magnetic field only, and it follows that the above experiment that current carrying conductor produces a magnetic field around it. Now, current carrying conductor produces a magnetic field. That moving charge means the moving charge is going to create a magnetic field. So this is a very important point. A moving charge creates a magnetic field. A moving charge or current sets up or creates a magnetic field in the space around it. Okay, the space surrounding it. So this was the Oerstead experiment. Now, based upon the Oerstead experiment, we have just understood that there will be some magnetic field. So now we have to find the strength of the magnetic field. Okay, what is the magnitude or the strength and the direction? So we have to find two things. We have to find the magnitude and the magnitude of the magnetic field, and then the strength, direction of the magnetic field. Okay. Now let us first understand the strength before moving to this Biot law. Let's understand the direction first. Now, for to understand the direction of the magnetic field, you have to use right hand rule. What do you have to use? Right hand rule. There are few other rules also, as in Ampere's swimming rule and something like that. You will find in different books. There are a few other rules as well, but the right hand rule is the simplest one, and this is what you are going to use. So for the right hand rule, obviously you have to use your right hand. Okay. Now, if you see your right hand, four fingers and the thumb. Okay, the four fingers and the thumb. So you see the thumb. Okay, the thumb becomes the direction of the current. Okay, thumb becomes the direction of the current, and the fingers will become the direction of the magnetic field. So thumb is the direction of the current. Everybody do like this: thumb direction of the current, and finger is the direction of the magnetic field. So if you see, your fingers actually can curl. Your finger can curl like this. Okay, fingers can curl like this. Now, if you get such situation, then what would be the direction of the magnetic field? You see that this is the current. Let's say this is the current I. So if you put your right hand in this direction, okay, if you put your right hand in the direction, that means your thumb in the direction of the current. As I just told you, thumb the direction of the current. So your four fingers will be in this like this. Okay, this will be a 4 fingers. So you see the thumb is actually moving in the direction of the current. It is in the direction of the current, and your fingers, if you look closely, is actually what? It is going down. Okay, it's going down. Your fingers are going down. Okay, so when the fingers actually goes down, what happens? It actually is showing the direction to be like this. Okay, it is showing the direction to be like this. So basically what happens is the direction of the magnetic field is like this. Okay, now this is somewhat hard to visualize. Again, you have to practice this. You have to practice this. What will be the direction of the magnetic field? For example, if the current is going like this, so you will have a direction of the magnetic field going like this. Okay, like this. This will be the direction of the magnetic field. Now, because you will be drawing this on your notebook, and notebook is obviously a two-dimensional plane, so 2D plane. So in that 2D plane, how would you represent a direction which is coming up or down? So that is represented as something called a cross. Okay, cross and a dot. Okay, cross and a dot. That means if you place your thumb in this direction, if you place your thumb in the direction of the current, then you will see your 4 fingers would be pointing inward to the plane here on this side. Okay, and this would become the cross direction. Okay, this would become a cross direction, that is magnetic field getting into, and then this would become a dot direction, that means magnetic field is coming out from this plane. So magnetic field getting into the plane means the cross direction, magnetic field coming out of the plane means a dot direction. Okay, cross direction and dot direction. So need to practice this. Draw these figures in your notebook right away and practice this right now before moving on. Pause the video and practice this right now so that you get this nicely. Place your thumb. Place your thumb in the direction of the current. Okay, on your notebook, draw these figures. Place your thumb in the direction of the current and then figure out the direction of the finger. Your finger in the first case, in this case, you will find that your finger would be pointing inward. That means this is a cross direction. Magnetic field is getting into this point and it is actually coming out from here. So this will become a dot direction. Okay, this will be a dot. Dot means magnetic field coming out, going into the plane like this. Okay, like this. So this is your magnetic field here. Similarly, in this case also, here you will get cross direction, here you will get dot direction. In this case also, the same, here you will get cross direction, here you are going to get dot direction. Here you will get cross direction and here you get dot direction. Pause the video, draw these figures, figure out yourself what is the direction. You should be very clear to it before moving on. Now, these are the direction of the magnetic field when the current carrying conductor is a straight line. Okay. So if I draw a straight line conductor like this, or like this, anyway, straight line conductors, this is what you're going to use. But in your junior classes, I hope you all remember in the CBSE, ICSE, State Board, any syllabus, junior classes, it is taught, magnetic effect of current topic is taught. And at the same time, something like this is also taught, isn't it? This something like there is a clockwise current. Okay, and then there is an anti-clockwise current. Let's say an anti-clockwise current. So for an anti-clockwise current, you will have a north here, and a clockwise current, you will have a south here. I hope you remember that. This is taught in your junior school. Now this is also done by using right hand. The previous right hand rule is also valid, and this right hand rule is also valid. Both are valid. In this right hand rule, what you need to do is to change this current and magnetic field. In the previous right hand rule, when we were only finding for a line wire, then this was your current and this was your magnetic field. Now this will become the magnetic field. Thumb will become the direction of the magnetic field. That means the direction of the north, specifically the direction of the north, and this will become the direction of the current. So if you put this into the clockwise and anti-clockwise, so when you put it for the clockwise, when you put it for the clockwise current, you will find that the thumb is pointing towards you. That means that is the reason why I have drawn a north here, because if I put my fingers in the direction of this, in the direction of the current, then I will find my thumb would be pointing towards me, and that will be a north. And if I do the other way, if I make my fingers in an anti-clockwise direction, then I'll find that my thumb is pointing inward. That means that side, the inward side is the north, and the side that I am into is become south. Okay, the inward side becomes north, and the side that I am into will become south. So again, there are two different uses of right hand rule. Don't forget that the right hand rule can be used making this as the current, this as the magnetic field, when the conductor is a straight line. Okay, conductor is linear. But if the conductor is a curvature, if the conductor is a curvature, doesn't matter half semicircle or quarter circle or any arc, if as soon as the conductor become a curvature, then you have to use this thumb as the direction of the north and fingers as the direction of the south. Pause the video, write this down, go again, rewind a few minutes back, again look at the same thing. This does not settle down in your head so easily. It will take some time. Okay, so pause the video, think about it, draw this diagram, get this mental memory clear before moving on, or else you will not be able to understand anything in this chapter. This is super important to proceed. If you have already understood it, practice a few times, and if you done, then let us move on to the next, that is finding the magnitude. Okay, finding the magnitude of this magnetic field. We have understood the direction of the magnetic field, so we are going to find the magnitude of this magnetic field. Now magnitude of this magnetic field is dependent upon this Biot savart law. Okay, it's a very simple law, Biot savart law. Now Biot savart law is a law which is used now. This law this law is used to determine the direct magnitude of the magnetic field, but the whole law is only valid or used for the small current element. I mean, the law itself is only for the small current element. Okay, so first Biot savart law is used to determine the magnetic field at any point due to a current carrying conductor. For example, if I have a current carrying conductor like this, if I have a current carrying conductor like this and some random point here P, okay, some random point here, then what is this conductor going to make the magnetic field at this point? That means what will be the magnetic field at this point due to this conductor? This is what we are going to find, or this is what the Biot-Savart law is going to explain it to you. Okay. Now, as I said, the Biot-Savart law is although for the infinitesimally small conductor. It is law. The law itself is for the small conductor, but we can use it for the long conductor also by doing some mathematical integrations, and we can do it. Now, to understand this law, first you have to understand something called a current element. Okay, current element. Now, what is a current element? Consider this conductor. Okay, consider this conductor. Look very closely. In this conductor you will find that there is a current which is flowing in this direction. Okay, and this conductor is not a straight line, so I am going to use a very small part of the conductor. You see a very small part of the conductor AB, which I will say that this is DL. Okay, the DL is small length. Now this becomes the product. It is current element is the product of the current and the length of the infinitesimal small segment of the current carrying wire. So what is current element? Current element is the product of the current that is flowing in the circuit times the length dl. Okay, 10 times the length dl. Now the interesting part is that this current element actually becomes what? It becomes a vector. It is a vector. You see, current is not a vector. Current is not a vector, but current element is a vector. As in area vector, I hope you remember, area was not a vector, area was a scalar, but area vector is a vector. So here also is that the current element is a vector quantity, and it has a direction. It has a direction that is same as that of the direction of the current. So what is current element here? Current element is I into dl. Okay, I into dl, and this whole thing is a vector. So you need to draw vector on the top. So this becomes your current element. Now Based on this current element, what will be the value of the magnetic field of this point? So let's draw this circuit. Let's draw this current and this point here P, and I'm supposed to find the magnetic field here at the point P. Now, magnetic field is written as B with a vector on the top. So this is the symbol for magnetic field. It is written as B. Okay. Now, first I will take a small current element here. Okay, I will take a small current element here of dl. Okay, so my current element become idl and it's a vector. Now from this idl there will be a distance from this idl to where, to this point. This distance, let's say, is r. So the position of this point with respect to this idl is a distance r, and this is also a vector. So we call this as a position vector of this point with respect to this idl. Okay, so idl is also a vector. Okay, idl is also a vector, and r is also the vector, and there is an angle between them. Okay, there is an angle between them because idl is a vector, so this vector will have some direction. The direction of the vector will be the direction of the current which is flowing in idl, and this is the angle here, theta. So what is the theta here? Theta is the angle between idl and r. Okay, r is the position vector of this point with respect to idl, and idl is the current element. Theta is the angle between them. Okay, so this idl is going to create a magnetic field here, and I'm going to call that magnetic field as db. Not the whole b, not the whole b, but only db. That means I'm going to only calculate a small magnetic field created by only this current element. A small magnetic field db only created by this current element. Okay, only created by this current element. So this db is equal to mu naught by 4 pi. So what is this? We'll discuss it, don't panic. Mu naught by 4 pi idl sine theta by r square. So this is my Biot law, the whole formula. So let us break down this formula and understand this. Now this part of the formula is a constant. Okay, as you have done before. Okay, I hope you all remember that in the electrostatics, everywhere in the electrostatics you have used ideal 1 by 4 pi epsilon naught. Remember, 1 by 4 pi epsilon naught value you have used. Here you are going to use this as a constant k as mu naught by 4 pi. So this mu naught by 4 pi have a certain value, as in 1 by 4 pi epsilon naught has a value of 9 into 10 raised to 9. So this will have a value mu naught by 4 pi. Mu naught by 4 pi will have a value of 10 raised to minus 7 Tesla meter per ampere. So how does this Tesla meter per ampere comes in? We'll discuss it, don't worry. So for now, just understand the value of this mu naught by 4 pi is 10 raised to minus 7, and it is a constant. Then dB is proportional to the, you see, dB is proportional to the magnitude of the current. First, magnitude of the current. That means the magnetic field here will be proportional to this current. Stronger the current, here, more will be the magnetic field. Very simple. Okay, then dB is also proportional to sine theta here. Okay, dB is also proportional to sine theta. Now sine theta, what does it mean? Understand this very carefully. That, let's say, if this is the current, if this is the current conductor and this is the point P. Okay, this is the point P, and this, you are taking this as a small dl current element, and this is your position vector of the point P with respect to dl. Now here you see that the angle between the dl vector, this one and this one, is happens to be 90 degrees. That means magnetic field here is proportional to the sine of this 90 degrees. That will be maximum magnetic field. Okay, maximum magnetic field. But if you are going to consider the point here, okay, if you consider the point here and try to calculate the magnetic field here, then you will find that dl will be in this direction, and the position vector of this point will also be in the same direction. That means theta will become 0, and here magnetic field will also become 0 because it is proportional to sine theta. Sine of 0 is 0, and this magnetic field will also become 0. So what can we conclude? That magnetic field will be 0 along the line of the current carrying conductor. If you have this as a current carrying conductor, that means magnetic field be 0 on all these points. Okay. Anywhere along the line of the current carrying conductor, magnetic field will be 0. And whenever you are considering magnetic field for a point which is perpendicular to the dl vector, so that it will be maximum magnetic field, and for all this point it will be zero magnetic field. dB will become 0. So very important that the magnetic field itself depend upon the angle theta. And what is angle theta? Don't forget, the angle theta is the angle between the dl and the r vector. Okay, angle between dl and r vector. So our Biot-Savart law, dV is equal to mu naught by 4 pi. Again, this is a constant, and I dl, the current element, sine theta, and then inversely proportional to r square. Inversely proportional to r square, very similar to the Coulomb's law, and gravities are all similar inverse coil laws. Coulomb's law, gravitation force, and this magnetic force, they're all inverse coil laws. So they are all following this square inversely proportional to the r square. So this is your Biot-Savart law. So in the Biot-Savart law, eventually you are going to get dB is equal to mu naught by 4 pi ideal sine theta by r squared. Now, if you just change this r square to r cube, think like this. If you just change this r square dB, yeah, this r square into r cube, and put an r on the top again. So if you put on the r on the top again, then the numerator here will become idl r sine theta. Now dl and r vector, dl r sine theta will eventually become dl cross r. I hope you remember vectors, cross product of two vectors. So cross product of two vector was a cross b will be is equal to ab sine theta, that you know. So here it will become what? It will become idl cross r. You see, idl cross r. So the idea is that the direction of the magnetic field is basically a cross product between the dl vector and the r vector. Between the dl vector and the r vector, the direction of the magnetic field is a cross product between the dl and the r vector. Now, how? Let us again find it. So let us say this is my dl vector. Okay, dl vector, the current element vector where the current is flowing, and this is the position of the point I want to find the magnetic field, and this will become my r vector. So if you use the right hand rule for the cross product, not the right hand rule just now we did in this chapter, not this right hand rule. So there are a few different right hand rule. Don't get confused. I am talking about the right hand rule for the cross product. Remember A cross B, B cross A. So you'll do A cross B upward and B cross A like this. You have done that before. So here that is what we are going to do. So if you put your hand in the direction of DL vector and come towards the R vector. Okay, so you cannot put your hand like this and come toward the R. You don't go the bigger angle. You go the smaller angle. I hope you remember that. So you have to put your hand like this from the DL vector and move towards the R vector. You will see your thumb would be pointing inward, and that you already know that the direction of the magnetic field for this current conductor will be across here. Okay, cross here and a dot here. You already know that. That means if you do this dl cross r, you will actually find your thumb pointing inward at this direction. But for this case, if you do r cross dl cross r here, if you do the dl cross r for this case, you'll find that your thumb would be pointing in the upward direction. So here this will become the direction of the magnetic field is a cross product between the dl vector and r vector. Okay, so do this in your notebook a couple of times so you get this very clear idea, because later on you will find many numericals where you have to find the direction of the magnetic field given the value of dl and r. Okay, so this point has to be very crystal clear. So our Biot-Savart law, again, Biot-Savart law, this part was our constant mu naught by 4 pi idl sine theta by r square originally. Then we made it r cube and r on the Numerator, it will become a ideal sine theta, mu naught by 4 pi ideal cross by r cube. So that is what my final formula is. Now, maximum and minimum value of the magnetic field we have understood. The maximum magnetic field is going to happen at theta is equal to 90. Minimum is going to happen at theta is equal to 0 degrees. Where on all these points, on which point the minimum is going to happen? Again, along the line of the conductor, minimum magnetic field, perpendicular to the line of conductor, maximum magnetic field. Okay. Now, magnetic field, you will find that the magnetic field definition in your CBSE NCERT content, you will find that magnetic field definition is given in 4 to 6 different ways. Okay. Magnetic field can be defined with respect to the force between the conductor, with respect to the current, and with respect to different things. So you will find magnetic field will have different definitions. Okay. So here we are going to define the SI unit of magnetic field from the Biot savart law. Okay, later on you will find that as again magnetic field we will describe or define in the terms of something else as well. So the SI unit of magnetic field is Tesla, and it is made it is named after the famous scientist Nikola Tesla. Very, very, very important, very great scientist Nikola Tesla. Okay, so Tesla is the SI unit of magnetic field. Now, if you put in this formula, if you put all the values, that is this, you make I as 1 ampere current and DL as 1 meter and theta as 90 degrees, so that this whole sine theta become 1, and R also as again 1 meter. And then you do this, then you will find that the dB will be is equal to mu naught by 4 pi, and mu naught by 4 pi has a value of how much? It has a value of 10 raised to minus of 7 Tesla. Okay, so there's 10 raised to minus 7. That means the magnetic field, you see, 1 Tesla is 10 raised to 7 minus 7 times the magnetic field produced or deduced by the conducting wire of 1 meter carrying a current of 1 meter at a distance of 1 meter from it. So what does it mean? That if you have a conducting wire, okay, this is a conducting wire, and at a distance of 1 meter, okay, at a distance of 1 meter from the wire, and the wire length is also 1 meter, the length of this wire is also 1 meter, and the current which is flowing is also 1 ampere. Okay, 1 ampere. So 1 ampere flow current flowing in a 1 meter long wire at a distance of 1 meter from it. So the magnetic field here will be 10 raised to minus 7 Tesla. So magnetic field compared to one single current wire is very small, and that is one of the reason why we don't experience strong magnetic field from the wires around us, because when they are a singular wire, and the magnetic field created by 1 ampere wire is pretty small, 10 raised to minus 7 Tesla.